Section 2.8 talks about one-to-one function and their inverses. Oh, why is this so big? Okay, that's fine. So, a one-to-one function is a function. Remember, a function is a relation in which the first coordinate does not repeat, namely the x. So, a one-to-one function must be a function first, in which the second coordinate does not repeat, the y value does not repeat. So when they say, in example 1, determine whether each function, they're telling you that this is a function. You don't have to check if it is a function. They're asking, is it one-to-one? Well, you look at the y values, 2, 3, 5, 5, whoa, those are different points, not one-to-one. It is a function, but it's not one-to-one. Why is that? Because y equal 5 has multiple x's. If I look at the second example that they have, we have, again, I look at 2, 3, 5, 6, automatically it is one-to-one. So again, if they tell you it's a function, you don't have to check the first coordinate. You just check the second coordinate. And the last example, example C, if we look at 2, 3, 5, it is one-to-one. And that's pretty much it as far as points. So here we're going to do the same. Same as when we did functions, given points. We're not going to do a map. Given points, given a graph, given an equation. Tell me whether this is a function. Tell me whether this is one-to-one. And then we're going to deal with what's known as inverses, which is extremely important and a big deal for us. So, since y cannot repeat, if I put those points on a grid, you could see with ease what's going on. If I put these points on a grid, 1, 2, 2, 3, 3, 5, and 4, 6. Those are functions because, you know, they satisfy the vertical line test. And I notice no one y give multiple values. If I look at the problem that wasn't a function, and I look at it graphically, I'll notice that 1, 2, 2, 3, 3, 5, 4, 5, and 5, 5. I notice they satisfy the vertical line test, but 1y, namely y equal 5, has multiple x's. So from this arise the horizontal line test, which is still the same definition in theory. A function is a relation in which a one-to-one function is a function in which the second coordinate does not repeat. Graphically, I'm looking at a horizontal line. Basically, if I'm given a graph and I'm asked is this a function or not, what I do, I sketch a horizontal line. If the horizontal line crosses more than once, it's not a function. Otherwise, it is. So, if I look at the first graph, and let me use, let's go with this. If I draw a line right there, again, I notice for that one y there are two x's. This is not one-to-one. And that's how we denote one. You could write one-to-one, it's just longer. Much quicker to just write 1-1. That's really what it's reserved for. I look at number part B. Well, it's a bit tricky because if I draw a horizontal line right there, you'll notice that it intersects an infinite amount of times, not one-to-one. But if I look at C, no matter where I draw my horizontal line, it's going to cross exactly 1. So we say that is one-to-one. So given points, given a graph, and given an equation. Now there is a definition in the book, you're welcome to look at it, which states the inverse of a function represents one-to-one if when x1 equal x2, f of x1 does not. That's a really complicated definition. We get around it by graphing. When they say an equation of a function is given, determine if it is one-to-one. Well, these are all functions. I sketch a graph. A parabola shifted 1 unit to the left. That kind of reinforces my knowledge of graphing. And I use the horizontal line test, and I notice this is definitely not one-to-one. And that's how we do this. Fairly simple. graphing should be beyond us now. We should be able to graph anything in no time. If I look at this graph, a cubic shifted 2 units to the left, 1 unit down. Something like this. Well, does that satisfy the horizontal line test? Well, yeah. Anywhere you draw a horizontal line, it only crosses once. So we say it's 1 to 1. Yes, it is. And radical, square root of x looks like that. When you multiply it by a negative, it reflects. And the 3 shifts it 1, 2, 3 units up. That graph looks like this. If I draw a horizontal line, again, no matter where I draw a horizontal line, it only crosses once. X squared plus 1 is a parabola shifted up 1 unit. That's definitely not 1 to 1, but there's a restriction. It states we would like a color that shows clearly. Let's go with that one. It says x is greater than or equal to 0. We're not looking at this piece. So only that right half. Well, that right half by itself does satisfy the horizontal line test, and that would be 1 to 1. That is correct. Now we get to the second portion of this lesson, and that's really what we're going after, an inverse. Now, an inverse is not opposite. An inverse is undoing your steps. Big difference. So we tie, this book ties the inverse to a 1-to-1 function. Other books don't, but the majority of the books do. The inverse of a 1-to-1 function. So if I'm talking about an inverse, it has to be 1-to-1. We denote that by the negative 1 power. Is a relation that interchanges the coordinates. So if in y equal f of x I have a point a, b, in the inverse I swap them. X becomes y and y becomes x. So something that we need for calculus is what I'm going to start with. Assume f and g are 1-to-1. Assume those are 1-to-1. Find the following. And this, even though once you get it, it's going to look really easy, it's extremely important for second semester calculus. The way you're going to play around this, you're going to really do this. Keep in mind, if this is a, this is f of a, and if this is a, this is f inverse of a. So, if I look at what I'm given f. I'm given when x equal to y equals 7. If I go and look at that in the inverse, those will switch. So when the problem is asking what is the y value in the inverse, when x equals 7, what would you say? You would say the inverse of 7 is a 2. Now, when I get to part B, I'm going to play the same game. And I always start with g and the inverse. So this is a, g of a. This is a, g inverse of a. So those are y values. When they say in the inverse, when x equal negative 1, the y equals a 5. All what you have to do is undo what we did right there. Switch the x with the y. This is asking what does y equal when x equal 5 in the g. That would be a negative 1. If you're thinking we just swap those, you're missing the point of why we're doing this in the first place. And if I look at this problem, and this is basically where you need it, you're going to have to do something like that. Well, again, I am going to play this game the same every time. When it says in the inverse, if x equal 9, find me the y. If I switch the order, because I'm given f, wouldn't that be 9 and f inverse of 9? No. So basically, doesn't that say, you don't have to worry about that part, but doesn't that say that this x equal 9 becomes y equal 9? Well, put a 9 there and solve. Swap those. Oh, I'm sorry, not 9. Let's go for 1. I made those up. Swap those. And how do you solve that? If you square both sides, you get x equal 4. So this says I have 4, 1 on this graph. That's true. If you put a 4 right there, 2, 3 minus 2 is 1. In the inverse, doesn't that mean that this point is going to become 1, 4? So when they say what is the y value in the inverse, I know I got to alter that one too. I'm sorry about this. I made it up. I thought I didn't see the negative there. There we go. It's asking when x equal 1, what does y equal? Well, the inverse of 1 is actually, the y in the inverse is a 4. So anytime they ask me something about an inverse, I have to make the connection that I just did. And how about the next problem? This is the graph of f. The graph of a function is given. Use the graph to find the following value. They want the inverse. Well, let's see how this works. If I'm looking at the inverse, so in the inverse, we want 0, the inverse at 0. Well, doesn't that mean in the original, we're setting y to equal 0? Y equals 0. Isn't that the point 2, 0? So when I go to the inverse, don't you swap those? 2, 0 becomes 0, 2. So the inverse, f inverse of 0 is a 2. Again, this idea is needed not in first semester calculus. It comes up in second semester calculus. And it's a must. And how about this problem? Well, the same deal. If I look at the inverse, if I'm thinking in terms of inverse, x equal negative 3. And there's the y. Well, doesn't that mean in the original f, y equal negative 3, y equal negative 1, negative 2, negative 3, right there. If y equal negative 3, isn't x a negative 1? When I do the switching for the inverse, doesn't that mean that the y value in the inverse is going to be a negative 1, which is the original x? The swapping part that we mentioned. So I find the point and I switch the coordinates. When it says here, in the inverse, I want to know if x equals 6, what does y equal? Well, aren't you going to go to the original, which is f, and you say, let's swap them. If y equals 6, 1, 2, 3, 4, 5, 6, it's that point. That point is actually 4, 6. So doesn't that mean the inverse, f inverse of 6 is actually a 4? And what if I get another value? What if there are two values? Which one do I give? If you have two values, that wouldn't be a one-to-one relation. If they say find the inverse, they're telling you that this is a one-to-one. Actually, I'm going to alter that. A graph of a one-to-one function is given. Alright. We'll do this as we go, so you know. There it is. Now what? Now, find the inverse of the given function. Okay, well, let's see. It says here, the inverse of a one-to-one function is a relation that interchanges the coordinates. So how are we going to do this? Well, we're going to follow that definition. How do you find an inverse? You're going to interchange the coordinates. You're going to say x equal 3y minus 1. And instead of writing x equal 3, the inverse, because that's really messy to carry, we just keep it like that and convert it at the end. So if I want to solve, this is the inverse. How would I solve? I'll add 1 to both sides. And if I divide by 3, that would be the inverse of my original function. Same deal with part B. Well, we could say x equal the inverse, because when you switch x with y, That is the inverse, but it seems to be a bit of a hassle to track that. What we do, we just say, let's write it as y, and we will take care of business in a minute. So cross multiply. Remember, you're solving for y, which is the inverse. Swap those. Factor a y out. And y would equal 3x divided by x minus 1, which is the inverse of x. Now, something very important about an inverse. If I said find the domain and range, we know domain is allowable x values. Range is kind of hard to see. But if I find the inverse of a function, the domain of the inverse is the range of the original. That's something to keep in mind. And if I look at this parabola right there, I know that parabola right there is not 1-to-1, but since they restricted the domain, it is 1-to-1, but I have to keep in mind, again, a simple graph will give away what's happening. X is -1, less than. So it looks like this. Domain, -infinity to 0. Range, if you look at the graph, -1 to infinity. Well, if I switch x with y, add 1 to both sides, and square root both sides, I run into a small dilemma. That's not 1-to-1. Well, that's why it's important to look at the range of the original must be the domain, and the domain of the original will become the range. If I want the range to be from -infinity to 0, let me look at the graph of this. Isn't the graph of y equal radical x plus 1 and y equal negative that looks like this? If I want the range to be -infinity to 0, shouldn't I take the minus? And if I just take, instead of plus or minus, just the negative, that would be 1-to-1, and that's how you figure it out. Same deal here. If I look at this problem, I switch x with y, subtract 2 from both sides, square both sides, and y equals x minus 2 squared plus 1. But I do know that this is not 1-to-1. I know from the graph it's not 1-to-1. So what I do, I look at the original graph. And that's why graphing is so important. I shift 1 unit to the right, 2 units up. The domain is that x is bigger than or equal to 1. The range is that y is greater than or equal to 2. So, doesn't the range of the original become the domain of the inverse because you switch x with y? If you restrict x to be bigger than or equal to 2, then this is a 1-to-1. And that would be my actual inverse. The original must be 1-to-1 and the inverse must be 1-to-1. Now they follow a trick which we don't follow. Again, they do their own things and we do our own thing. That's okay, this is going to be out of sync. They have a definition that says a graph of a function, and it's, oh my goodness, I'm stuck in calculus, so you guys forgive me, and it's inverse. A graph of a function and its inverse are symmetric with respect to the line y equal x. What they do, they draw this line y equal x, and they kind of say, well, look, what you're going to do, you're going to imagine that you're going to paint F, and you're going to fold the page about the red line, and you're going to tell me what the image is, there's an easier way, much easier way, to sketch the inverse. And let me pick a color. Let's see what we're going to use. Let's go with brown. We're going to switch x with y. We're not going to use this. We could, but it's easier. Isn't this point -1, -3? Switch x with y. Isn't that -3, -1? This point is 0, -1. Switch x with y, -1, 0. There's a line connecting those. This point is 1, 2, 3, 0. Switch x with y, 0, 3. And this point is 1, 2, 3, 4, 1, 2. Switch x with y, 2. I ran into the problem itself, but it's all good. And there it is. Except that should be a line. There. If I look at the graph, this line right here, again, I could reflect it, or I could say, you know what, this is 0, 1. Switch x with y, that's 1, 0. Right? And this point seems to be about 1.20, 0, 1.2. Connect those with a straight edge or a ruler, and that's the inverse. So we're going to stick with one definition. How do you find the inverse? You switch x with y. Done deal. How about this graph? Well, if I look at this graph, this is the point 0, 1, switch x with y. This point looks like as if it's 1, 2. It's not, but let's say it is. So 2, 1. And this point looks like it's -1 about 0.6, 0.6, -0.1. And if I sketch a graph of that, there's the inverse. And the same deal with this graph. This is the point -2, 0, 0, -2. This is the point -1, -1. So if we switch them, we get -1, -1. And if I move, this is like the point 1, -1.5, -1.5, 1. If I connect those with a smooth curve, there's the inverse. Nothing to it. And the last aspect of this lesson says if f and g are inverses of each other, if you take the composition, you will get x. Basically, they undo each other. That's very important. There are two ways you could verify. You could find the inverse yourself and say, look, this is the inverse. Meaning, take this, switch x with y, and find the inverse. But to practice this, given two functions f and g, determine if they are inverses. Again, you have an option. You could switch x with y and solve for it and show that you get this. I'll accept that, that's fine. But to practice this, we take f composite g, and it's a good practice. That is f of g of x. That is f g of x is 2 over x minus 5. So replace this x by that. So instead of dividing, I could multiply by the reciprocal. There it is. And to go the other way around, g composite f of x, that is g of f of x. That is g of f of x is 2 over x plus 5. Take this now and put it in for that x. That is 2 over x plus 5 minus 5. The 5's cancel out. That's 2. Instead of dividing by a fraction, I could multiply by the reciprocal and I'll get an x. Same deal here. If I take f composite g of x, that is f of g of x. Again, for practice, that is cube root of x plus 7. Plug that in there. Cube root of x plus 7 cubed minus 7. Those cancel out. And g composite f of x. So you have to show both. If you chose to take this path, you have to show both ways. X cubed minus 7. Now take this and put it in for g. That is the cube root of x cubed minus 7 plus 7. The 7's cancel out. And the cube root of x cubed is x. Of course, you could out of mind, say, well, let x equal y cubed minus 7. I think that's a lot faster. X plus 7 equal y cubed, so y equal the cube root of x plus 7, and you could say that's the inverse, and there it is, and it matches. That's a lot quicker, but I just want to make sure that you know how to do this and you are aware of this because of some theoretical problems. And that's pretty much it for this section.